Good day everyone, I am Sharlyn Vargas, your instructor in mathematics. So for today's lesson, we're gonna learn about Euler's theorem. So before we proceed, let me give you a background about Euler's theorem. So Euler's theorem is presented by Leonard Euler, correct me if I'm wrong about my pronunciation, on August 2, 1736 and published on 1741. So Leonard Euler is a Swiss mathematician, physicist, astronomer, geographer, logician, and engineer who founded the studies of graph theory and topology and made pioneering and influential discoveries in many other branches of mathematics. So he was born on 15th day of April 1707 at Basel, Switzerland, and he died on 18th day of September 1783 at Petersburg, Russia. In definition, if n and a are relatively prime with open interval a and n is equal to 1, then a raised to quotient of n congruent to 1 modulo n. Let n be a positive integer. A quotient of n is defined to be the number of positive integers not exceeding n that relatively prime to n. To continue, Euler's theorem have four rules. Rule number 1, p minus 1 where p is a prime. Rule number 2, p raised to n minus p raised to n minus 1 where n is a prime power. Rule number 3, quotient of m multiplied to quotient of n. Rule number 4, n multiplied to the quantity of 1 minus 1 over p1 times the quantity of 1 minus 1 over p2 times until the quantity of 1 minus 1 over pk. So we have to understand better, we have example. So we have here 2 raised to 193 modulo 23. So since 23 is a prime number, we're gonna use the rule number 1. So quotient of 23 minus 1 is equal to 22. So equals the quantity of 2 raised to 22 raised to 8 times 2 raised to 17. So we have 1 raised to 8 multiplied to 131,072 modulo to 23. So the answer is 18 modulo 23. Now let's move to example where we can apply Euler's theorem. So Euler's theorem can used in reduced large powers modulo. So example, find the last digit of 55 raised to 5. So we're gonna write 55 raised to 5 modulo to 10. So since 10 and 55 does not relatively prime, but 55 have a prime power decomposition which is 5 and 11. So to continue, 55 raised to 5 is equal to 5 raised to 5 times 11 raised to 5 is equal to 5 raised to 5 times 11 raised to 4 times 11 equivalent to 11 raised to quotient of 10 equivalent to 1 modulo 10, 5 raised to 12 times 1 raised to 4 times 11 equivalent to 34,375 equivalent to 5 modulo 10, 11 raised to 4 equivalent to 1 modulo 10. So take notes, the quotient of 10 is equal to 4. That's why we have 11 raised to 4. So hence the last digit of 55 raised to 5 is 5 because 34,375 last digit is 5. So another example, find the last digit of 3,333 raised to 4,444. So we're gonna write 3,333 raised to 4,444 modulo 100. So the quotient of 100 is equal to the product of quotient of 2 raised to 2 and 5 raised to 2 is equal to 2 times 5 times 4 because 2 times 5 times 4 is equal to 40. So to continue, we have here 3,333 raised to 4,444 equivalent to 3,333 raised to 40 raised to 111 multiplied to 3,333 raised to 4 equivalent to 1 raised to 111 multiplied to 3,333 raised to 4 modulo 100 is equal to equivalent to 33 raised to 4 equals 1,185,921 equivalent to 21 modulo 100. So the last digit of 3,333 raised to 4,444 is 1 because of 1,185,921. The last digit here is 1. So I hope you learned something about my discussion about Euler's theorem. That's all. Thank you.